Welcome back, students. After so many days, we are meeting here and we are continuing the chapter that we were studying in last videos, that is electric fields, electric charges and fields. Actually, the chapter we are studying. So, the next topic that we have is a small derivation, that is torque acting on a dipole placed in an electric field. Correct? So you know what is torque and what is electric field, right? In first year itself, you have understood what is torque and what is the reason for torque and what are the conditions to have torque. And you have studied in earlier videos what is electric field. So today we are studying torque acting on a dipole placed in an electric field. If I place a dipole in an electric field, in a uniform electric field, what is the torque acting on that I am studying now. So we are going to see that equation. We will be deriving that equation now. So let us see what we have to do first. First we have to draw this diagram. Here what we have is a dipole. So what is the condition to have a dipole? Dipole means what? It should contain two equal and opposite charges. So here you can see plus q, here minus q. Two equal and opposite charges. They are separated by a small distance. This is A, this is A. Total is 2A, correct? They are, this plus q and minus q are separated by a small distance 2A. So this is a dipole. And you can see the direction of electric field here. This E is uniform electric field in this particular direction. So this dipole is placed in this place where the electric field is uniform, E. Okay. So if I measure the angle between the direction of electric field and dipole, that is theta. That is theta. Okay. At the center of dipole, I have measured the angle. I got the angle as theta. Okay. Now, if I complete a triangle here, like ABC, triangle ABC, this angle is also theta. Mathematically, you know that this angle is also theta. These two lines are parallel. These two lines. So this angle is also theta. So this dipole, as you know, as all dipoles contain two charges. When charges are placed in electric field, what happens is there will be electric force acting on the charges. So if I consider plus q first, there will be a charge on this plus q. That is why you can write as F equal to q into E. Q into E. Q is charge, E is this electric field. This is acting in this direction. I have shown the direction also. And there will be force on this minus q also. That will be in downward direction like this. So minus q into E. This is the force on minus q. And you also know that the direction of dipole moment, that is shown here, from minus q to plus q. This is the direction of dipole moment represented by P. Okay, this is all about the diagram we have. I think I have explained all the things related to the diagram. You know that, right? Next, I am writing this here in sentence under that. While writing the derivation, we need to do that. That is, force on plus q is q into E, and force on minus q is minus q into E. Okay. Next. So if I consider the net force acting on the dipole, net force means total force acting on the dipole is QE, that is plus QE minus QE, right? So the second force is minus QE. So magnitude are same, that is why force is equal to 0. So the net force acting on the dipole equal to QE minus QE, two charges plus QE and plus Q and minus Q. So net force, total force will be 0. Net force is 0 because E is uniform. E is uniform. But these forces act at different points, correct? No? Two forces are acting at two different points because the dipole is separated by two charges. In a dipole, two charges are separated by a small distance or 2a. That is why couples are acting. So it satisfies the condition to have a torque. Correct? It satisfies the condition to have a torque. Therefore, there will be a torque on the dipole. There will be a torque on the dipole. What is that torque? What is the magnitude of that torque? That we'll see first. Then we'll see the direction or vector form. Finally, we'll write the equation in vector form. So initially, we need to find the magnitude of torque. So how to represent torque? Torque is represented by tau. Correct? Tau. So this tau equal to force into perpendicular distance between the forces. Force into perpendicular distance between the forces. Not the actual distance between the forces. The distance should be perpendicular. Perpendicular distance between the forces. Direction of forces. Okay. So here this force is represented by F and BC is the perpendicular distance. You can see here. Correct? See here. The perpendicular distance is BC. This is the direction of minus QE and this is the direction of QE. So the perpendicular distance will be, this is BC, correct? So this force is, magnitude of force is F and the perpendicular distance between the couples, the two forces, is BC. That is why this is F into BC. F into BC. So what is the next step? So here, in this particular case, what is BC? That is the question. What is BC? So yes, in triangle ABC, this triangle ABC. If I take sine theta, this is theta, sine theta, that will be BC by AC. BC by AC, correct? BC by AC. Here, sine theta equal to BC by AC. So what is BC? Just bring this AC to the side. So it will be BC equal to AC sine theta. AC sine theta. So what is AC? See again, AC, the distance between the two charges in the dipole. A plus A, 2A, correct? AC is 2A. AC is 2A. So I have here 2A sine theta. 2A sine theta. Therefore, magnitude of torque, tau, equal to QE. What is that QE? The force, F into BC, correct? So BC we got 2A sine theta. So F is QE, magnitude of force, into 2A sine theta. 2A sine theta. QE 2A sine theta is tau, magnitude of torque. So what is this? By simplifying, we can write it as PE sine theta. What is P? P is dipole moment. How to represent dipole moment? 2AQ. 2AQ. P is 2AQ. That is why this Q 2A is P. What is remaining is PE sine theta. Tau equal to PE sine theta. P is dipole moment. E is the magnitude of electric field. And theta is angle between E and dipole. Yes. Therefore, in vector form, finally, you'll have the vector form tau, vector tau equal to vector P cross vector E. Why it is cross? Cross product. So this torque is cross product of dipole moment and electric field. P cross E. Tau equal to P cross E, correct? So P cross E. Why it is cross means we have sine theta here. A cross B. A is AB sine theta, right? Similarly, P cross E is PE sine theta. That is what you call as torque. So what is the direction? From, you know, how to find the direction of cross products. A cross B, how to find the direction, that is very familiar to you. So here you can tell the direction of this tau is outside the plane of paper. Outside the plane of paper. Okay, this is what is all about torque acting on a dipole placed in an electric field, the derivation. So final equation, you know, okay, tau equal to P cross E. So this is what the total derivation is. You can read it once again, you can write it, you can have a notes. It is also important. Okay, thank you for watching. Keep watching. We'll meet in the next video.